All right, we are now looking at Chapter 9. And Chapter 9 starts off with properties of radicals. So a radical is like a root. The root that we have used is a square root. We'll also use other kinds of roots, but we'll start off here with square roots because that's what we are used to. So starting off here, right here, we got a radical expression is an expression that contains a radical. Remember the word expression here, that means that there's not necessarily an equal sign, right? So if you look at any of this, like problem 1 there's no equal sign, so that's just an expression. Otherwise, it would be an equation, and there'd be an equal sign in there. A radical expression is considered to be in simplest form when no radicals have perfect nth powers as factors other than 1. And I'm going to show you as number 1. That's going to be what we do for example 1. You know what? Let's just go ahead and look at it right now. Number 1, we've got the square root of 147. We want to simplify. And we're not going to put it such that we have a decimal, right? We could write in a decimal, but we're going to take the number 147 and we're going to try to break that apart. We're going to try to factor it. So I'm going to take 147 and I'm going to look for numbers that I can divide by that would be able to multiply 147. So my tricks that I use to decide what should I try out. So I have my calculator handy here. I've got 147 typed in. And I'm going to divide by something. I don't want to divide by 2 because that 7 makes the number odd. For 3, the way I check 3 is I say, well, 1 plus 4 plus 7, that's 5 plus 7, which is 12. 3 has this funky rule to where if the integers, or if each of the separate numbers add together to be a multiple of 3, so 12 is a multiple of 3, so 147 is going to be a multiple of 3. And that's a weird rule. Not all of the numbers follow that. I think maybe 6 follows that also. Or not 6, maybe it's 9. I don't know. The only one that we're looking at right now is just 3. So I know I'm going to type in my calculator 147 divided by 3. And whenever I type that in, I got 49. 49, I'm going to do the same thing. 49 is 7 times 7. Now, what I'm going to look at here is I'm going to break up my radical, and I'm going to have him be 3 times 7 times 7. We could write this as the square root of 3 times 7 squared. And then I'm going to rewrite that again as root 7 squared times root 3. You know, and some people would like to leave that 7 squared as a 49. That was what we had right there. I like to break it up into actual, the farthest factors we can do. Oh, you know what? I didn't say. I stopped at 3 and the 7s because those are prime. If they were not prime numbers, then I would keep trying to go on and on and on. The square root of 7 squared is just going to be a plain old 7. And the square root of 3, we're going to leave him as the square root of 3. So this is now the simplest radical form version of 147. Now, one way, sometimes we like to write all of this up here, and sometimes we don't. Whenever we want to skip it and we want to use the shortcut here, we look back at our factor tree, and you know the tree is it's called a factor tree, and these bottom pieces, you know, we maybe call them the leaves, right? The 49 is maybe like a joint where it branches off, but the 7s are the actual leaves. So because we're dealing with a square root meaning like 2, we look for 2 numbers that are duplicates. We have a duplicate 7s right there. And then we go through and circle all of our duplicates. And then we circle our singletons. And we have a singleton 3. The duplicates, so like the 7, came outside. And when they were outside, it's just a single one. The 3 is just a singleton, so he stays underneath. So that's the way that I normally do these, and I'm sure we'll do a couple more. Let's go back up and read our next number here. So that was all just exercising problem number 1 here. Or not problem, but the rule number 1. Numbers 2 and 3 both deal with fractions. Number 2 says that a radical can't have a fraction inside of it. So that would be like example 3 down here. There's a square root with a fraction inside, and the fraction has an 11 and a 36. Number 3 is that no radical can appear in the denominator. Okay, and these are old math grammar rules, right? So the first one was that if you can break it apart like we broke apart number 1, we have to break them apart. Number 2, we can't have a fraction inside of a radical. And number 3, we can't have a radical in the denominator of a fraction, right? Those 3 rules, the process of making an expression follow those 3 rules, is called rationalizing. Radicals with the same index and radicand are called like radicals. So whenever we're looking here, the index of a root is right here. Maybe I can write that a little bit better, like that being like an n. That would be called the index. For us, that's a square root so far. Right? On all these, you look back at example 1 down here, the square root of 147, you could say that there's a little 2 there if you wanted to. Kind of like just the understood if you have an x, there's like a 1 hanging in front of him. There are other kind of roots, like a cubed root or something like that. The radicand is the piece underneath it. So in example 1, the radicand was 147. Conjugates can be used to simplify a radical expression that contains a sum or difference involving roots, and we're going to do that later on. There's also the product and quotient properties of radicals, or square roots, or any kind of radical. If you have a root A, B together, you could split them up and have root A and root B, and that's what I did down here with the root 7 squared and the root 3. I split it up. Maybe even more importantly here is you can break them up over a fraction. So like in example 3, we can kind of see how the A and the 11 match together. So this, we'll go ahead and do example 3 here. The first thing we're going to do is split it up and have root 11 over root 36. If we go through our rules that we had here, rule 1, 2, and 3, we just satisfied rule number 2. There is now no fraction that is inside the root for number 3 here. Now we look at just kind of simplifying the radicals using example 1, or problem 1, not problem 1, rule number 1. There we go. The square root of 36, that is a perfect square. So that's 6, and we still have the root 11. And now this is just fine. That's a good answer because it satisfies all 3 rules. Remember, the first rule is that if you can break something apart, you can. So the 11, we can't break him apart because 11 is a prime number. So rule number 1 is taken care of. Rule number 2 is that you can't have a fraction inside the root, and we don't have a fraction inside the root. And then rule number 3 is that you can't have a root in the denominator, and we do not have a root in the denominator. So that's it. That's example 3. Let's look down at example number 2 down here. Now this one, we have numbers and variables here. So the 25, that is a perfect square, right? If you broke 25 apart, you got 5 and 5. That's a pair of 5s, and they come outside. So this is equal to 5 root x to the 5th. And then in the beginning, whenever we're doing these, I think about that x to the 5th, and I'm going to write it out. I've got 1, 2, 3, 4, 5 different x's. And just like whenever I make my factor tree, so here's my x to the 5th, he broke apart to be all of these, right? I circle my pairs. I have 2 pairs and then a singleton. So I had a 5 on the outside still. Then I have an x. I have another x. And then I have my root and I have my leftover x there. So prettying that up a little bit, I'm going to say that I've got 5x squared root x. And that's going to be my answer. Example 2 here really only relied on rule number 1 that we had above, because rules 2 and 3 had to deal with fractions, and there was no fraction in here. All right, let's look over here, and I think this is number 4. Ooh, example 4. We look right here, and we've got an index of 3 now, right? So it's a cubed root. So we're still going to start this off by breaking it apart, just like we worked on example 1. But now we're not going to look for couples. We're going to look for trios. We're going to look for groups of 3. So I'm going to take my calculator out, and I'm going to take the number 135, and I'm going to divide it by 5, because that 5 being at the end means I could divide by 5. And I get 27. Now, some people if you notice it, 27 is a perfect cube because, not x, what did I want to say? I wanted to say 3 cubed is 27. If you recognize that factoid, that's awesome, and you can jump to your answer being 3 cubed root of 5. And that's going to be our answer. Let's see if I can write that a little bit better. 3 cubed root of 5. That's our answer. That's only if you really notice that that 27 is 3 cubed. Now, if you didn't notice it, we could take it and break it apart again. 27 divided by 3 is 9, and then 9 divided by 3 is 3. Now we look for trios, and we have a trio of 3's. They come outside the radical, and then we have a singleton 5, and he goes inside the radical. And there we go. Let's look at the next page here. Example 5. Now, we see that we've got a negative underneath our radical here. Now, oftentimes when we see a negative under a root, that means that we're done. We just say no solution, that's it. Because the square root of, let's say, negative 4, that doesn't exist. Negative 4, that doesn't exist because there's no two numbers, two of the same number, that can spit out a negative. You think about if you've got a positive number and a positive number, that's going to give you a positive number, right, when you multiply. What if we had a negative number and a negative number? Well, a double negative is a positive. So whenever we have square roots, and this can be generalized to any even numbered root, they have to be positive underneath it. But once you have a cubed root, let's say the cubed root of negative 8. So the cubed root means find 3 numbers that multiply to be negative 8. We could take 3 numbers, multiply by negative 8. It's going to be negative 2, negative 2, and negative 2. 2 cubed is 8. And then if you look at the negatives, we got 1, 2, 3 negatives. We have one pair, so the first 2 go positive, and then the last one is left over, and that's our negative in front of our 8. So with odd numbered roots, like a cubed root, you're allowed to have negatives, and the negative can just jump right outside of the radical. So right down here, I'm going to go ahead and start off by saying, well, this is a negative cubed root of y to the 4th over 1,000. Then I'll take care of the fact that right now we have a fraction inside our radical. So I'm going to break this apart and say we got a negative out front, then we have a fraction. The top is cubed root of y to the 4th. The bottom is the cubed root of 1,000. Now, cubed root of y to the 4th. Well, that means we have 4 y's, right? What y to the 4th is there's 4 of them multiplied together. There's going to be one trio, right? So here, let me write it out. 1, 2, 3, 4. One trio, and then a singleton. Now the denominator, cubed root of 1,000, that's going to be 10. And that's going to be our answer. All right, let's look. You know what? Let's go right to 8 right here. Oh, actually, you know what? Let me look down. Let's do number 6 here. Number 6, starting off, we are now failing rule number 2, meaning that there's no fraction inside of our radical. There is a fraction inside our radical here. So first off, I break them up. I say on top, we got a root 7. On bottom, we've got a root 2n. Now, I can't have a radical in the denominator, right? That's part of my rules that I'm not allowed to have that. So what I'm going to do is I'm going to multiply by a fancy 1. Fancy 1, like the number 1, right? And that's pretty ugly right there. Let's write that again. Fancy 1. We know that we can multiply any number by 1 and it stays the same, right? You can multiply anything by 1. And when you've got a fraction, if the top and the bottom are the same, so like 5 over 5, that's 1. So I can multiply by a fraction, and as long as the top and the bottom are the exact same thing, I'm really multiplying by 1. So I'm not really changing anything. So in this problem, whenever I decide what I want to multiply by, they're both going to be radicals. and they're both going to be the same index of our given radical. This has an index of 2, right? There's like a little invisible 2 right there. We normally don't write it, but it's there. So over here, our 1 is going to have square roots as well. And we want it to be such that our denominator will have a pair. So right here we have a singular 2, we want another 2. And then we have a singular n, we want another n. So now we'll have, and when we multiply across, the square root of 7 times the square root of 2n over the square root, and I'm going to put these together, and we're going to have 2 squared times n squared. Our numerator, let's go ahead and put those together and see what we got. Square root of 14n. And in our denominator, we have a pair of 2's. So there's 2 on the outside. And an n squared, the square root of n squared is going to be a plain old n. Let me make my pen just a little bit thinner. Oh, well, that didn't work. All right, it's not going to work. Number 9. Oh, actually, hold on. Let's do number 7 also while we're here. This one has the same problem as the last problem, except it's already got it to where the denominator is the only root. The numerator does not have a root in it. So what I'm going to first start off by doing is I'm going to break apart that 4 and say that we've got the cubed root of 2 squared, right? 4 is 2 squared. Now I'm going to multiply by a fancy 1 again. It's going to be cubed roots, because that's the radical that we have given. And then I want trios this time, because cubed roots want trios. We have 2 2's, right? 2 squared means that there's a 2 times 2 there. We need 3 of them. So I need another 2. That way our denominator will be just a plain old 2 when it comes outside, right? Because we'd have 2 2's and then plus 1 2 gives us 3 2's. All right, so there's 3 of them, and the cubed root of 2 cubed will be a plain old 2. And then our numerator, we have a cubed root of 2 as well. And now we just multiply straight across, 5 cubed root of 2. And there we go. Now one thing right here, when we write our index, our 3, we want to make sure that it's kind of in that little nook of the square root, right? So there's this little nook right there. We want to make sure it's sitting there, because sometimes people will write this as 5 cubed root of 2 like that. And that looks a whole lot like 53 square root of 2. All right, so we want to make sure that it sits in that little nook right there. That way we don't make it look like that. All right. I think we're ready to try out number 8 now. Now number 8, the denominator has a radical in it, which we just got done taking care of 2 problems where there was a denominator with a radical. But this one here is more different because there's a square root of 3 plus 1. Here, we're still going to use a fancy 1 like before, but our 1's going to have to be even more fancy. We're going to have to use what's called a conjugate. And a conjugate, hopefully that's spelled correctly, is going to be the binomial. So you copy this down, the square root of 3 and the 1, and you change the symbol in the middle. And I got to do the same thing on top, square root of 3 minus 1. And sometimes it's good to put these guys in parentheses here. Now right now this might seem silly, but we're just going to do it and it'll end up working out very nicely for us. Our numerator, I'm going to leave the 4 out front and the square root of 3 minus 1. Later on we'll go ahead and distribute that in, but not quite yet. Our denominator, now I have the square root of 3 plus 1 and the square root of 3 minus 1. In this next step, I'm going to take this square root of 3 and I'm going to distribute it. So my numerator, I'm going to leave b. My denominator, I have the square root of 3 times the square root of 3 gives me a plain old 3. Square root of 3 times negative 1 is negative root 3. 1 times the square root of 3 is positive root 3. And then 1 times negative 1 is negative 1. These two middle terms are going to cancel because it's the positive and the negative version of the same thing. So now we're going to be left with a 4 on top times root 3 minus 1 all over 3 minus 1, because those two middle terms canceled. And now we'll have 4 times the square root of 3 minus 1 all over 2. And then now, because this 4 is all alone times this guy, we can actually reduce this like it's just a plain old fraction. 4 divided by 2 is 2, and then I still have my root 3 minus 1. Right? And the only reason I was able to cancel there is because of these parentheses right there. If this over here was 4 root 3 minus 1, if it was that, you could not cancel because there's no parentheses and the 4 doesn't belong to the negative 1 then. But here, the 4 does belong to the negative 1 because it belongs to both of them, so we're able to cancel really easily. So part of that canceling is why I leave this 4 out. In the very beginning, we could have distributed, but I chose not to because I thought that at the end it might cancel out nicely. So I'd suggest that you also don't cancel out too early, or excuse me, don't distribute too early. Now my last step is to distribute, and it's going to be 2 root 3 minus 2. And that's going to be my answer. All right, scrolling down, let's do number 9 now. Now number 9, there's no fraction, which is very nice for us. But we do need to try to break this guy apart. 63, he is a multiple of 3, right? 6 plus 3 is 9, so yeah, divide by 3 and I get 21. 21 divided by 3 again is going to be 7. Now I know I've got this 5 root 7 over there. I'm just going to leave it be. Because they're split up with a plus, I can deal with them I can deal with them separately. And the root 7 is already prime, so this little chunk over on the left, he is already in simplest radical form. I'm working on the right side to put him in simplest radical form. I have a pair of 3's and a singular 7. So copy down the first part, 5 root 7, and then plus, the pair of 3's come outside, and they're a single 3 then, and then I have a square root of 7, or, well, that's 2, square root of 7 left underneath. Now, these are like radicals, the root 7 and the root 7. Because they are the exact same thing, you could combine like terms even more. So I'm going to treat this like it was 5x plus 3x. Well, 5x and 3x would be 8x. So over here, we're going to be able to say 8 root 7. And that will be my final answer for that one. Scrolling down once more, we're going to do that same process of what we did up here, where we simplify the radicals. So I'm going to start off by doing that. I know I've got my root 7 times this thing here. I've got my root 3, and I'm going to try to break apart my 48. I'm going to break it apart to the side here. 48 is what? 4 times 12. 4 is 2 times 2. 12 is 4 times 3. 4 is 2 times 2. And we have a 3 there. So I have a pair of 2's, another pair of 2's, and a 3. The 4 did not get circled because he's just where it like branches off. He's not the actual tip. You don't only circle the tips, the leaves. We have 2 2's on the outside, then we have a radical, and then we have a 3 underneath our radical. Prettying this up just a little bit, we'll have root 7 times root 3 plus 4 root 3. The root 3's are like radicals, so we can think about this as being like x plus 4x. Well, x plus 4x is going to be 5x. So here we're going to have root 7 is going to be 5 root 3. Right? There's like an invisible 1 sitting in front of that root 3, just like there's a 1 in front of our x there. And then lastly, we can multiply these radicals here, and we're going to have 5 square root of 7 times 3. That'll be 5 root, is that 21? I'm thinking that's 21. 21. There we go. All right, let's see. Is that our last problem? That is it. All right, so we want to go through these whenever you're doing on homework and whatnot. You want to try to go through them slowly. Don't rush too quickly. It's very easy to make an error when you're doing your factor tree. If you're not comfortable with your multiplication tables, rely on a calculator. Okay? Remember, we have 3 rules. Our first rule is to break things apart with a factor tree, if possible. And the second 2 rules deal with fractions. There can't be a fraction inside of your radical, and there can't be a radical in the denominator of a fraction. All right, that is section 1, properties of radicals.